A surveyor stands on the edge of a mountain plateau, his boots resting on a surface so flat it looks poured, not formed. The horizon runs in a straight, unwavering line. Behind him, the land drops away in a sudden vertical wall of stone, as if the top of the mountain had been removed in a single motion. The air is still. The rock beneath him is level enough to host a runway, a city, or a parade ground. Yet this place is not an airfield or a construction site. It is a remote summit, far from roads, machinery, or modern industry. And it is not alone. The official explanation is simple. Mountains rise through uplift and erosion. Wind, rain, and time grind peaks into plateaus. Rivers carve valleys. Glaciers shave ridges. Over millions of years, nature smooths the sharp edges of the earth into the landscapes we see today. Geology textbooks describe these processes in careful diagrams. Survey records catalog elevations and contours. The pattern is presented as slow, gradual, and predictable. The mountains were shaped by natural forces, and the flat tops are the final stage of that long transformation. But there is a detail that sits quietly in the margins of those records, a detail that repeats from continent to continent. Many of these mountain summits are not merely flat. They are level to a degree that engineers would recognize instantly. Their surfaces sit at nearly identical elevations across wide regions. Their edges form straight boundaries that extend for miles without deviation. Their rock layers end abruptly, as though cut rather than worn away. The shapes are not random. They are consistent. And consistency is where questions begin. There is a theory, rarely stated directly but often implied in technical discussions. It suggests that some landscapes may not be entirely natural in their present form, that certain plateaus could be the result of large-scale earth removal, conducted at a time when the record of such work was not preserved or was never formally documented. Not a dramatic conspiracy, not a sudden catastrophe, but a slow, coordinated effort whose traces remain in the geometry of the terrain itself. The theory does not claim certainty. It proposes a possibility, and it begins with measurement. Early surveyors were meticulous observers. They carried chains, compasses, and leveling instruments into remote regions long before satellites and drones. Their notebooks recorded distances to the inch and elevations to the foot. In many mountainous regions, those measurements revealed something unexpected. Summit after summit registered the same height above sea level, often within a narrow margin of error. Not 10 feet higher, not 20 feet lower. The numbers repeated. The pattern appeared in regions separated by hundreds of miles. What remains in the archives are tables of figures, columns of elevations recorded decades apart by different teams using different equipment. The data aligns. The summits form horizontal planes that extend across entire ranges. In engineering, such uniformity would suggest deliberate grading. In geology, it is often attributed to erosion acting evenly across a landscape. Yet erosion is rarely even. Wind favors one direction. Water follows gravity. Ice moves irregularly. Nature produces variation. The record shows precision. Photographs from the early 20th century add another layer to the observation. Black and white images captured by survey expeditions show broad, flat mountaintops stretching to the horizon. The edges are sharp. The surfaces are smooth enough to walk across without climbing. In some images, the plateau ends in a straight cliff face that runs for miles, unbroken by gullies or landslides. The rock appears sliced rather than fractured. The camera does not explain how the shape was formed. It simply preserves what was there. Geologists have studied these formations for generations. Their explanations focus on processes known as planation and uplift. According to this model, a region is worn down to a nearly level surface over long periods of erosion. Later, tectonic forces lift that surface upward, creating a plateau or flat-topped mountain. The theory is supported by laboratory studies and field observations. It accounts for many features of the landscape, but it leaves certain details unresolved. One of those details is the abrupt termination of rock layers at the summit surface. In cross-section diagrams, the strata appear to stop suddenly at the same elevation across wide areas. There is no gradual thinning, no uneven weathering. The layers end cleanly, as though a horizontal boundary had been drawn through them. In industrial settings, such boundaries are common. They are created by excavation equipment that removes material in controlled passes. The resulting surfaces are level, consistent, and repeatable. Mining engineers refer to this pattern as benching. Large machines remove rock in horizontal slices, creating flat terraces that step downward into the earth. The geometry is unmistakable: straight edges, level floors, uniform thickness. When similar shapes appear on a mountain scale, the resemblance is difficult to ignore. The dimensions are larger, but the pattern is the same. The surface looks worked. Transport infrastructure offers another clue. Many flat-topped mountains are connected to historical rail lines or roads that climb steadily toward the summit before ending abruptly at the edge. These routes often appear in early maps, labeled as service lines or access roads. Their purpose is not always explained. In some cases, the lines disappear from later editions of the maps, replaced by blank space or simplified terrain markings. The physical routes remain on the ground, but the record becomes quiet. What matters is the timing. In several regions, the construction of these transport lines predates the modern industries that would later dominate the landscape. The infrastructure appears before the documented need for it. The rails lead to plateaus that show evidence of material removal, yet there is little documentation describing the scale of the work. The pattern repeats across different countries and different decades. The locations vary, the geometry does not. The mainstream explanation deserves careful consideration. Natural processes can produce flat surfaces under the right conditions. Wind erosion in arid climates can plane rock into smooth platforms. Rivers can carve terraces along valley walls. Glaciers can grind peaks into level ridges. These mechanisms are real and well understood. They have shaped landscapes for millions of years. But they tend to leave irregular traces, channels, grooves, and uneven margins. The results are rarely perfectly horizontal across long distances. In contrast, many surveyed plateaus show a levelness that persists even after centuries of weathering. Measurements taken decades apart reveal minimal change. The surfaces remain consistent. The edges remain straight. The geometry holds. What erosion begins, time usually finishes. Yet in these cases, the process seems to have stopped at a precise boundary. The land reached a final form and stayed there. The pattern becomes more compelling when the scale widens beyond a single mountain. Across different continents, explorers have documented flat-topped ranges that share similar elevations and profiles. In some cases, the summits align along a horizontal plane that stretches for hundreds of miles. The repetition suggests a common process rather than isolated coincidence. The shapes echo one another across oceans and climates. Maps provide a quiet confirmation of this repetition. Topographic charts display contour lines that form large, uninterrupted loops around plateau edges. The spacing between the lines is consistent, indicating steep, uniform slopes. The summit contours form broad, featureless areas with little variation in elevation. Surveyors rarely describe these features in dramatic language. They record them as data. Yet the data carries its own message. Historical accounts sometimes mention large-scale earthworks in passing. Reports describe extensive quarrying operations that removed stone for construction projects or infrastructure. The quantities are measured in millions of tons. The work lasted for decades. In some regions, entire hills were dismantled to supply material for railways, canals, and cities. The documentation focuses on the projects themselves, not on the landscapes left behind. The transformation of the terrain becomes background information. What remains on the ground are vast, level surfaces where peaks once stood. The rock is gone. The shape persists. Over time, vegetation grows across the plateau, softening its appearance. New generations see a natural landscape. The memory of the work fades. The record becomes fragmented. What changed was the explanation. Institutional records reveal another subtle pattern. In several cases, survey revisions note adjustments to elevation data after new measurements were taken. The changes are small, often a few feet, but they occur across wide regions at roughly the same time. The updates suggest a coordinated effort to standardize reference points. Such standardization is common in mapping and engineering. It ensures consistency across projects. Yet it also creates the appearance of uniformity where variation once existed. The idea of coordination does not require secrecy. Large-scale infrastructure projects demand organization, planning, and communication between agencies. They leave traces in budgets, contracts, and technical reports. But those records are often scattered across departments or archived under different categories. Decades later, reconstructing the full picture becomes difficult. The pieces exist. The connection between them is obscured by time. Economic factors can also shape the historical record. Industries that remove large quantities of material operate under financial pressure. They focus on efficiency and output. Detailed documentation of every landscape alteration is not always prioritized. When operations close or ownership changes, records may be lost or condensed into summary reports. The absence of detailed data does not imply concealment. It reflects the practical limits of record-keeping. Still, the physical evidence remains visible. The plateaus do not erode quickly. Their surfaces endure. Satellite imagery shows their outlines with striking clarity. From above, the edges appear as clean, geometric boundaries against the surrounding terrain. The contrast between the flat summit and the rugged slopes below is unmistakable. The pattern repeats. Engineers studying modern excavation projects recognize familiar shapes in these landscapes. The scale differs, but the geometry aligns. Straight edges, level floors, consistent gradients. The resemblance suggests a common set of physical constraints governing how material is removed from the earth. Gravity, friction, and structural stability produce predictable forms. Whether the work is done by machines or by natural forces, the resulting geometry follows the same rules. Yet, there is a threshold where similarity becomes difficult to dismiss as coincidence. When multiple regions display the same pattern at the same elevation, the question shifts from how the shape formed to why it formed there. Why that height? Why that boundary? Why that consistency across distance? Some researchers have proposed that ancient landscapes may have been modified during periods of intense resource demand. Large populations required stone for construction, metals for tools, and materials for infrastructure. The extraction of those resources could have reshaped entire mountain ranges. Over time, the industrial origins of the terrain might have been forgotten, leaving only the altered landscape as evidence. Others suggest that the flat-topped mountains are remnants of older surfaces preserved through geological stability. In this view, the level summits represent ancient plains lifted upward by tectonic forces. The uniform elevation reflects the original surface rather than later modification. The explanation fits many observations, but it does not fully address the sharpness of the boundaries or the abrupt termination of rock layers. The debate continues in academic journals and field studies. Measurements are refined, models are tested, new data emerges. The discussion remains technical and cautious. Scientists weigh evidence carefully before drawing conclusions. The process is slow, deliberate, and methodical. That caution is a strength of the scientific method. It prevents premature claims. It also means that unresolved questions can persist for decades. Meanwhile, the landscapes themselves remain unchanged. The plateaus sit quietly above the valleys, their surfaces level and their edges precise. Travelers stand on their summits and look across horizons that feel engineered rather than accidental. The experience is subtle. There is no dramatic signpost announcing the mystery, only the geometry of the land. The stone remembers. The record is still there. The pattern does not disappear. What matters is not whether every flat-topped mountain was shaped by human hands. Many were not. Nature is capable of remarkable symmetry, but some formations display characteristics that invite closer inspection. They challenge assumptions about scale, time, and effort. They suggest that the history of landscape transformation may be more complex than the simplified narratives often presented in textbooks. In the end, the question is not whether mountains can become level through natural processes. They can. The question is whether all such formations share the same origin, or whether some represent chapters of human activity that were never fully recorded. The answer may lie in archives that have yet to be examined, in survey notes stored in forgotten cabinets, or in measurements waiting to be compared across regions. Until those comparisons are made, the flat-topped mountains will continue to stand as quiet witnesses to their own formation. Their surfaces remain smooth, their edges remain straight, their elevations remain consistent. The evidence does not speak loudly, it waits. And the real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.